All right. Hi guys, I'm Mr. Schrago.
I'm Miss Humphrey.
And today we're going to be doing your Unit 3.1 notes today.
Because it's the weirdest week ever.
Yeah, if you thought this school year was going to be normal, sorry.
Tricked ya. So you have 3 ways that you could do these notes, right?
Yep.
So we're going to share this document with you, and if you'd like to, you could type or use some type of digital recording of the notes on your computer. You could also, if you have access to a paper printer, you could print these notes out and then handwrite your notes in. Or what's our third option, Mr. Schrago?
I don't remember.
I do. You could just grab a piece of paper and just kind of jot these notes down on a piece of paper. And then when we're back together, you could staple the paper to your notes or copy and handwritten copy those notes from the paper to the packet.
Yeah. The key is we want you to be watching this video and transferring the information you're gaining to a new document of some type that you'll be able to submit to us later, because that's what we'll be looking for.
Love it.
Cool.
All right, get us started, Mr. Schrago.
All right, so we are talking about projectile motion. That's the whole theme of Unit 3. And today, the first thing we have to talk about is, what is a projectile, right? Like, you've probably heard the word before, and we always tell you physics is everywhere. Well, a projectile is any object that is only under the influence of gravity. And that means there's no applied force. So this is an object after it's left your hand, after it's been kicked by the person in football who kicks the ball, the kicker, I think, right?
Punter.
Sometimes. I was close.
Yep.
Or
after the bullet fires out of the gun, arrow goes out.
Yep. Anytime something's in the air, Thelma and Louise driving their car off the cliff.
Movie magic.
All projectiles. Now, with projectiles, since we know it's only under the influence of gravity and there's no applied force, that's going to simplify our lives a little bit. Because if we're going to draw the free body diagram for a ball that's dropped from the bleachers, well, it's under the influence of gravity. There's no applied force on it. And just for this unit, we are going to simplify our lives a little bit, because one thing we like to do in physics is sometimes simplify our model of how we're learning about it. And we're just going to leave the force of friction off of our free body diagrams when we're talking about projectiles. It's not something we're going to calculate, so we're not going to include it on our FBDs. So when we draw the free body diagram for a baseball on its way to the outfield, oh hey look, it's only under the influence of gravity.
Mr. Gagne, or Mr. Schrago, I want to pause you for 1 second. Isn't that baseball flying through the air this way though?
Right? But is anything pushing on it that way?
Nope, you're right.
Man. That is one thing that we oftentimes see students have a misconception about, is when something's moving, we want to add force arrows for the direction it's moving, but after we're done pushing on it, once it's a projectile, the only thing touching it anymore is gravity.
Yep.
That stunt car off a cliff, only under the influence of the force of gravity.
So the next question says, what force is common on all of these objects? Well, you know it by now. It's gravity. Mr. Schrago, I'm left-handed, so I'm going to trade sides with you.
You can tell we planned this out.
Yep. Yes, no applied force, no friction, conveniently, just gravity. And remember, how do we calculate gravity? Well, Fg is equal to mass times 9.8. And, force of gravity is also known as weight. And I have the silliest song that not everybody needs to memorize, but if you wanted to, you could. To calculate the weight, multiply the mass by 9.8. It's the coolest song.
It's definitely stuck in my brain after many years.
So force of gravity is mass times 9.8, which is the acceleration due to gravity on Earth. And really, this is channeling that F equals ma equation from Newton's second law. But we don't necessarily have to worry about that because we've got this other thing. And let's see, remember, you can have motion without a net force. That's almost kind of like a precursor in a second.
Yep.
I think we don't want to put anything there.
That's just like a reminder for when we look at the next stuff, I think, is why we put that there.
So Mr. Schrago, because this is your computer, I'm going to let you advance us to the next slide and begin our notes on the next day.
There we go.
Perfect. Do you want to do horizontal and vertical?
Yeah,
And then
let's do it.
I'll do horizontal data.
All right, guys. So in this unit, one of the key things that we need to do is we need to split up the two aspects of how a projectile travels. Because if we're thinking about a projectile, right, we're talking about an object that's going to kind of fly along. And the most common one is one that like went off a cliff, right? Here's our car. It drove off a cliff. And as that car is driving off that cliff over there, right, it's going to travel off to the side, but it's also going to fall down. And so we need to talk about the side-to-side portion of the motion. That's like how far away it fell from the cliff. And the vertical portion of the motion, which just means the up and down motion. Now, gravity, well, does gravity affect the horizontal or vertical? Has gravity ever pulled you into a wall? Has it ever made you just tip over randomly? It always pulls you towards the ground. So it only affects the vertical portion of that motion. Why not both?
Because physics.
Yep, that's something we're still, I mean, I like to say, researchers are still working on understanding the fundamentals of gravity. Maybe you're going to be the person who figures it out.
All right, so then that brings us to horizontal motion. I'll do this section, Mr. Schrago. So horizontal motion. Recall Newton's first law. Oh, my most favorite part of this is everybody has like a little different spin on how you say it.
We do.
So the way I like to say it is an object that is experiencing a force. Maybe we call that an action force. We'll experience then a reaction force. Opposite direction, but same value, same magnitude. So if I push on Mr. Schrago's actually pushing on me with the same amount of force, just in the opposite direction. Do you use any type of different version?
I do, but it's the same wording. I just tell a slightly different story.
Awesome. So recall Newton's first law. Should we just say for every force there's an equal and opposite force for now?
Yeah, I think so.
Okay. You know what I'm most excited about? Is I think I just nonstop talked about Newton's third law.
Yeah.
You know what? Mr. Schrago is going to tell you the Newton's first law because that was hilarious, and I'll write it as you talk
we're going to know
about it.
an object in motion remains in motion unless acted on by an outside force. So the way that this is going to apply to our horizontal projectiles, or just our projectiles in general, is that the side-to-side portion of the motion, well, once our car drives off that cliff, nothing is pushing it forward. Nothing is really fighting its forward motion because we're dropping air resistance for this. And so it really has no forces acting on it to the left or right. That means it's a balanced force. And when we have balanced forces, we'll just keep doing what we're doing, right? There's no outside force acting on it. So that car, however fast it's going when it drives off the cliff, that's how fast it's going while it's in the air.
This makes me think about the hockey puck hit on the ice.
Yeah.
That just floats on forever. Or have you ever seen like a science-y space movie where like an astronaut's like disconnected and just flies
Drifting off into space. Oh, 2001: A Space Odyssey.
Jeez. So yeah, I promise Ms. Humphrey knows the difference between the first law and the third law. But if you need to write this down really quickly, an object in motion remains in motion unless a force is applied.
And a good thing to remember is we always care more that you understand the idea than which number goes with which one.
Mm-hmm. So we're going to use our constant velocity equation, x equals vt. It's not speeding up, it's not slowing down, so there is no acceleration.
And now that we're away from the first unit, we're just going to drop that x naught, that x0 part.
Yes.
This is what we'll probably be using a lot from here on out.
Yep. So we have our constant velocity graphs. If you remember for constant velocity, we're going to see that I'm going to just do right now for convenience, I'm going to do positive direction, if that's okay.
And we we understand by now that you should hopefully be able to see what a constant negative velocity would look like. We'll just always use positive for our horizontal.
So as it's traveling in a constant velocity, what we see is every second of time that goes by, the same distance is covered. So every unit of time, the same distance is covered, so it's a linear line. And if we wanted to get technical or remember stuff from last unit, that slope is the actual speed. For our velocity time graph, we've said, okay, it's a constant speed, cruise control's on the car, never ever changing, staying the same value the whole time. Yes.
Constant velocity, constant value.
Awesome. And there's a tiny little note here, and if you're using just a piece of paper, I wouldn't write this down. All projectiles have the same horizontal motion. The only difference is their velocity.
Yep.
Awesome.
And we'll just always be sketching that velocity graph. So if you're starting to worry about slopes and getting that part right, what we're looking to see there is that you remember that the horizontal portion of the motion is constant velocity.
Ah, yes.
We're
Mr.
not gonna make you
Schrago,
plot it.
I think you better go through the vertical one for us because I obviously have a little bit of a case of the Mondays.
Oh my. Me too.
All right,
All
you
right.
do this section and I'll do this Bob and Louise question.
Sounds great. So, when we are talking about the vertical part of that object's motion, we're going to see a couple different things, right? If we're talking about an object that's been thrown up in the air, just tossed upwards, right? It's always hard to do that and have it stay on the camera. Now, we have to take a look at a couple things it's doing, right? When we first throw it, it's an object, it's traveling up towards the top of its motion. Then, for one brief moment, you can kind of see there's like that distinct peak to its motion as I throw markers everywhere,
You're good at that.
and that's the top. And then it's going to fall back down into our hand. Now, one thing we know is that here on Earth, the acceleration due to gravity is always negative 9.8 meters per second squared. Now, one thing that people often forget, or they feel like they aren't okay with, is that at the top, even though that marker looks like it briefly pauses, its velocity might be 0 at the top. It does briefly come to a stop as it travels up. That acceleration is always going to be negative 9.8 meters per second squared, no matter what it's doing. The vertical acceleration is always that.
If I wanted to use words to describe the motion and the traveling on the trip up and the trip down, what would be the words like for velocity maybe?
Well, I think on the way up, our velocity would be decreasing, right? We're going to slow down on the way to the top, and then increasing on the way down. Remember, it's increasing in the negative direction as it travels down. It's speeding back up into our hand. Otherwise, it would just hang out at the top where it's stopped.
You know, Mr. Schrago, it's at this point that I think about how our learners are so good at this type of learning mechanism.
Yeah.
You know, you guys have had so much experience with this. And a reminder is, though, you can always pause this video if you need to copy something down that Mr. Schrago's writing, and then, like, restart it for yourself. You don't need to be speed writing everything that we're doing.
Yeah, and take advantage of that. That's actually one thing we were talking about just the other day. That's a major advantage of the online format. Is when you're just watching us in a video, hit pause. You're unsure? Hit pause. Or turn the speed up if we're going a little too slow and we're rambling.
Yes.
What equations do we have for an object that is changing speed? Well, we have your standard 4 equations that you're going to use throughout physics class. However, the most common equation that you are going to see in this unit is going to be x equals 1/2 at squared plus v1t. You might remember, we've used this equation a lot for whenever we drop an object, right? So when we're dropping an object, we're going to find that with horizontal projectiles, that up and down part of the motion, it's a lot like dropping it. And so we're going to use that most of the time. Any of the 4 equations, they work. But you're going to find that you're almost always going to be using this part of it.
So, Mr. Schrago, I love interjecting. And one thing I'm really thinking about, because, yeah, it's going in this, like, horizontal motion, but also vertical. What I think I heard you say is that in the vertical motion of it, V1 is 0?
Ooh, I forgot to mention that, but you know, you're
write that
totally
down.
right, you know?
Oh, yes.
This is an object dropped scenario. And I think we'll even ideally maybe have watched a bullet dropped versus a bullet fired at some point in here. And you'll have seen that if we drop something, or if we shoot something out of a gun, it's going to fall at the same rate. These horizontal projectiles, the up and down portion, is just like dropping something.
Yep. That'll be a really common place where sometimes kids like forget it. And so we want to really make sure we're practicing it and being reminded of it every time we do these
In
problems.
fact, you might also want to make sure you then write that down.
Yes.
Because we're not going to explicitly remind you, it's like by entering it as a given in the math always, but it's going to be there. right? You're going to need to remember the vertical part, the up and down part of that object's motion will always be governed by these properties.
Yes. You keep doing that. I'm just writing something random here.
Now, right here, if you're looking at the graph, we're going to graph only the vertical part. That's a typo we have here. That last page was the horizontal part of the object's motion. Here, we're only going to graph the vertical part of the object's motion. What I think is really great about graphing the vertical part of the object's motion is the xt graph is going to look kind of like the path that the object would take. It's kind of nice. Now, that comes from the fact that our object is accelerating in the negative direction, right? It is, if it's driving off a cliff, it's driving along and falls on down. And that fall, right, that's our object speeding up in the negative direction as it goes down. Over here, we'll start out at 0, and we're going to gain negative velocity on our v t graph. Over here, this is our xt graph.
Do you want to know like a secret, like a little fact about physics?
Ooh, yes, I would love to know one.
Definitely nothing that you need to memorize, but did you know the slope of this line is actually negative 9.8?
Right? Isn't that kind of cool?
Physics!
I love you guys so much. Wait, can we get guest appearance?
Get over here,
We
Miss
got a
Silverman!
guess for the Bob and Louise problem
Miss
right
Silverman's
here.
gonna do the last question. Miss Silverman, I know she has not proofread this question at all, so if you need a little jogger, like memory jogger, we're here.
Oh my god, this is teamwork makes the dream work, right? Alright, so I'm gonna read it. Bob and Louise are throwing pumpkins off their balcony to dispose of them in the dumpster below. Bob dumps his pumpkin straight down off the balcony, while Louise throws her pumpkin horizontally off the balcony. Which pumpkin hits the ground first? Okay, so let's think about this. So here is the balcony, and maybe we'll do Bob in purple, right? And Bob, I'm just drawing a little visual. I like visuals. Every teacher's different. So Bob's just going to drop his pumpkin straight down, and let's say the ground is right here, okay? And then Louise is then going to stand in the same spot, so exact same spot, right? And she's going to throw hers directly horizontally. And which hits the ground first? Well, when we're thinking about like the time it takes for a projectile to hit the ground, what really only matters is the vertical distance that it falls. And we know that they're both being like dropped or thrown from the same height. And so what I can assume is that because the acceleration due to gravity is going to be the same, it's not like one magically is on Jupiter or something, they're going to fall at the exact same time, which definitely seems counterintuitive, right, Ms. Humphrey?
You know what is exciting? We have like a whole Mythbusters video that we're going to link later on, and we'll show you that video so that you can even like just be in awe of these facts.
It's just a really cool video too, and you've got a whole week at home.
Yay!
Mr. Schrago, you better get over here. Mr. Johnson's in Canada, so that's why he's not here.
Is this how you spell vertical?
Canada.
You know what? It's not, but it's okay.
Oh no!
You know what?
Well,
It's AL.
You know,
Should we redo this whole video now, Miss
definitely you should redo the whole video.
I told one of
Guys.
these Lazarus.
I think we'll be okay. They're all watching this from home.
Have a good day.
Bye, guys.
Bye.
We'll see you next week. You gotta click stop.
That was